Okay, welcome everybody. Today we're going to go ahead and talk about lesson number 13. This is section 2.2, which is all polynomial functions of higher degree. So yesterday, of course, we focused on the quadratic in particular. That's degree 2. We're now going to kind of extend upon that to include polynomials of any degree. To get us started, let's talk a little bit about general polynomial behavior. And you can see I have two little sketches there for you. First and most important is that all polynomial functions are continuous. That means they are nice, smooth curves. That means there are no breaks or gaps. That word continuous basically means that you could sketch the entire graph without picking up your pencil. The idea of whether or not a function is continuous is actually a huge idea in terms of calculus. So we're going to talk a lot more about that later in the week. The second thing that's worth noting is that every increase in degree number gives one additional turn of the graph. You can see that I put turn in quotation marks there because that's actually what it's called. If I skip ahead to the next slide for a second, this is a reminder of what the polynomials from degree 0 to 5 look like. What I mean by turn, okay, if you look at the first function, which is constant, that's just a horizontal line. That's not really a curve. Then a linear function, which again is diagonal, but not so much a curve. If you go ahead and take the quadratic function, for example, which is degree 2, if I was to sketch my quadratic, and then I wanted to turn it from degree 2 to degree 3, I would go ahead and turn back down. So there would be another turn. If I wanted to go ahead and make it into a quartic, I would turn back up. If I wanted to turn it into a quintic, I would turn back down. So these here are the turns, just to kind of make sure you understand what that word means. Then if I go back, the maximum number of turns is the degree number minus 1. So what does that mean, maximum number of turns? Well, consider the two following quartics. So let's say I had y equals x to the 4th minus 4. And then let's say I had y equals x to the 4th minus x squared. So both of these are quartics. But if I was to go ahead and graph them using the procedures we're going to go over shortly, x to the 4th minus 4 would actually look kind of like a quadratic. It would have a y-intercept of -4 and only 2 x-intercepts because 2 of them would be imaginary. If I was to compare that to the graph of x to the 4th minus x squared, that graph would actually look like such. And it would go through the point 0, 0. So when I say the maximum number of turns has to be the degree number minus 1, that means it could be less, but it can't be more. So if you take a look at x to the 4th minus x squared, the degree, of course, is 4, and there are 1, 2, 3 turns. If you take a look at x to the 4th minus 4, the degree is 4, but there's only 1 turn, and that's perfectly fine. So the maximum number has to be the degree minus 1. So the maximum number in this case would be 3, 1, 2, 3. But again, there can be fewer. There just can't be more. Again, refer back to this slide if you need to remind yourself the general shapes. And of course, as you go from degree 5 to 6, you again just continue to turn and turn and turn, however the graph tells you to. Going back for a second to that idea of being a continuous function, again, we're going to talk more about that later in the week. But normally, when they tell you that a function is continuous, they tell you that it's continuous from some value to some value over some interval. So here's an example of a function that's continuous from a to b, happens to be a straight line. Here's a function that's continuous from a to b, and it happens to be a curve. Doesn't matter. Those are both continuous functions. Here, another example of a nice, smooth, continuous function compared to a function that is discontinuous. And we would actually say that there are discontinuities. And that, of course, is because there's a break. You'd have to pick up your pencil in order to get to the second piece. We actually call that a jump. And we're going to talk more about that again later in the week. Very important idea in terms of calculus. So then to remind you of something called multiplicity. Multiplicity is how often a certain root is part of the factoring, and it has very big implications for the graph. So if you take a look at the example in question here, x minus 5 cubed times x plus 7 times x minus 1 squared. Again, you could certainly write it out longhand like this, but it's actually much more beneficial to leave it the way it is. Because of the fact that x minus 5 is the factor, that means that positive 5 is the answer. X plus 7 means -7, and X minus 1 means +1. Remember, of course, it's always the opposite. Then, depending on what the exponent is, which of course there's always a 1 there if there's nothing, that tells you the multiplicity. So you'd have a multiplicity of 3 at the root of 5, you'd have a multiplicity of 1 for the root of -7, and you'd have a multiplicity of 2 for the root of +1. Just to reiterate, the word root is synonymous with the word 0, is synonymous with the word x-intercept. All three of those things mean the same. I'm going to use them interchangeably, so you do have to make sure you know that they all mean the x-intercept. Once you've identified the multiplicity, and again, to abbreviate, feel free to say M3 for multiplicity 3, M2 for multiplicity 2, and so on. Here's what it actually means for the graph, and I'm going to go ahead and start by talking about what happens if the multiplicity is odd. So again, if you look at the left-hand side of this table, this would be x plus 3 to the first, so that would have a multiplicity of 1. Because this is x plus 3, the root is, of course, the opposite. What happens at a multiplicity of 1? Well, the graph always just goes right through. So it either can go from a negative to a positive, or from a positive to a negative. So anytime you have a root with a multiplicity 1, your graph simply crosses the x-axis. In the next example, you have x minus 1 to the third power. That would, of course, give you a root of +1. And basically, when you have an odd degree of 3, 5, 7, they kind of do the same thing. So this table calls it a squiggle and then a pass-through. I actually tend to call it a flatten and then a pass-through. Some people call it an inflection point. Perhaps there's other words to describe it. I don't really care what you call it as long as you can do it. But notice here that at +1, the graph would clearly kind of get flat near that answer, and then it would cross through, again, either from the negative to the positive or from the positive to the negative. And any odd degree bigger than 5, 7, 9 has the same behavior. It kind of just gets flatter and flatter as the degree increases. What if there's an even multiplicity? So x squared, that would have an answer of 0. That would have a multiplicity of even 2. And anytime you have a multiplicity of 2, I like to call that a bounce. So that means it would touch the answer and then go back in the same direction it came from. So positive, it would touch it and stay positive. Negative, it would touch it and stay negative. So I like to call that a bounce. Then if you had x plus 4 to the fourth, -2. So for any even degree, 4, 6, 8, and again, getting bigger, it still bounces, but it kind of makes a flatter bounce. So again, you can look here in the picture. You see how the bottom is much flatter than it normally is. But again, you have to touch it, and then you have to go back in the same direction that it came for. So still a bounce, but just a flatter bounce. All of these diagrams that I'm showing you here, I've put them in the class notebook. That way you can refer to them because obviously it's a lot for you to write down. So don't feel like you have to rush to keep up. I promise I'm going to put all these diagrams into the class notebook. So then end behavior is the other important thing you need when it comes to polynomials. And end behavior is based upon two things: the degree of the polynomial, whether it's even or odd, and the sign of the leading coefficient. So a little note about the degree, which is why I have this table for you. You can either be given a polynomial that's in standard form, which means it's been multiplied out, or you can be given a polynomial in factored form, which means it hasn't been multiplied out. When it comes to the sign of the leading coefficient, I think you would agree, whether you look at the left side of the table or the right side of the table, you can clearly look out front to see whether there's a positive or a negative. So positive, negative, positive, negative, again, for both sides. You just want to be careful when it comes to the degree. If you're finding the degree in standard form, it's the biggest exponent only. So degree 2, 2, 3, 3. Biggest exponent only. If it's in factored form, you're going to find the degree by adding up all the x's, including their multiplicities. So this would be x to the first, it would have a degree of 2. X to the first, it would have a degree of 2. X to the first, that would have a degree of 3. X to the first plus x to the squared would have a degree of 3. So again, each side of the table, the two polynomials are the same. One is just in standard form and one is just in factored form, but it is important that you know how to find the degree from both of those forms. Once you are able to figure out the degree and the sign of the leading coefficient, these are the 4 types of end behavior. Oops, sorry about that. And again, you are going to see this diagram again in your or my highlighter here. You are going to see this in your class notebook, so don't feel like you have to rush to write anything down. So going along the top for the degree, there's even and odd. Going through whether the sign of the leading coefficient is going to be positive or negative, there are the 4 types of end behavior. You're probably used to them as up, up, down, 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 up, and up, down. But so not only do you want to be able to know them by those names, but you also want to start adding, again, a little bit of honors to it and a little bit of calculus to it. So let's go ahead and start, for example, with this box right here. So this is up, up, and behavior. And this is the result of positive and even. And then here are a bunch of examples that would be positive and even. Not only is the end behavior up, up, but here's how you would say it in kind of a calculus-y way. As x goes to negative infinity, y goes to positive infinity. That means that as the x's get small, the y's get big. As x goes to infinity, y goes to infinity, means as the x's get big, the y's get big. Just in case I didn't say that right the first time, the first one says as the x's get small, the y's get big. And then the second one says as the x's get big, the y's get big. And that's where the whole up, up, and behavior comes from. If we take a look at this box over here, this is going to be odd positive. So the way you say that end behavior is down, up. And again, here's the way you would say it in the fancier calculus way. As x goes to negative infinity, y goes to negative infinity. That means as the x's get small, the y's get small. As x goes to infinity, y goes to infinity, means as the x's get big, the y's get big. So that's where the idea of end behavior comes from. You are going to have to get used to using that fancier infinity notation, maybe not stating it so much as actually being able to recognize it. Let's go through the last 2 while we're here. So this is an example of a box that is negative even. So that's down, down. Here's the fancy way. As x goes to negative infinity, y goes to negative infinity. So that means as the x's get small, the y's get small. As x goes to infinity, y goes to negative infinity, means as the x's get big, the y's get small. Last but not least, this is your odd negative. So that end behavior would be up, down. As x's get small, y gets big. That's what that first statement says. As x's get big, y's get small. That's what that second statement says. So just very important that you understand where the end behavior actually comes from and how it relates to the infinities. And again, this diagram is in your class notebook. How are we going to put all that together? So it's possible that based on last year, you're used to graphing these using the graphing calculator. Obviously, I'm not going to have a way to stop you, but next year, it's very possible that you're going to have to be able to do all that using without using the graphing calculator. So I think it's important that we practice that. So I'm going to ask you here in these examples is the same thing that I'm going to ask you tonight. You're going to try to graph them without a graphing calculator by finding the end behavior and then the x and the y intercepts. So when you go to graph, you're going to always go ahead and start by factoring. So I'm going to go ahead and factor out the greatest common factor, which is x. Then I'm going to go ahead and factor again. So factors of -5 that add up to be -4. So here's my complete factorization, x times x minus 5 times x plus 1. In terms of the end behavior, it's easier to look at standard form. That is odd positive. So odd positive is down, up. Each of the x-intercepts come from factored form. So the x-intercepts are going to be 0, +5, and -1. Since they're all to the first power, those are all going to be multiplicity 1. To find the y-intercept, it's easier to use standard form. Put a 0 in for all the x's, and you get a y-intercept of 0, 0. And then how do you put all that together to make the graph? Well, you go ahead and start by graphing everything you know. So an x-intercept at 0, -1, and 5. The end behavior, down, up. Because these are all multiplicity 1s, that means you cross at the x-axis. So starting from the bottom here, I go through -1, go up a little bit, back to the 0, go down a little bit, and then ultimately back through the 5. Remember, because this is a continuous function, once I plot those points, I should be able to connect it with a nice smooth curve. If you're wondering to yourself, how high do I go? How low do I go? Those are important questions, which we are going to address soon. But for now, you can just make a sketch, which means you can just estimate. Excuse me, let's go ahead and try this next one. So negative x to the 4th plus x squared. Just by looking at this problem right here, I can say that this is even negative, which means the end behavior is going to be down, down. I can also see that if I plug a 0 in for the x, I'm going to get 0 for the y, which is the y-intercept. When I go ahead and factor it, I like to say when in doubt, take the negative out. So not only am I going to take out an x squared, I'm actually going to take out a negative x squared. That's going to leave me with a positive x squared minus 1, which luckily for us factors again as the difference of squares, x plus 1, x minus 1. Then to find the x-intercepts, of course, you set it equal to 0. The negative x squared is going to give you an answer of 0 with a multiplicity of 2. And then negative 1 and 1, which have multiplicities of 1 each. I would advise you not to write plus or minus, only because I think that that can sometimes make it difficult. People confuse plus or minus with multiplicity of 2, so try not to make that mistake. Plot everything you know, which is actually only 0, 0, negative 1, 0, and 1, 0. And behavior, down, down. Because of the fact that you have x-intercepts that are reflections of each other over the y-axis, that's how you know that this graph should have y-axis symmetry. So coming through the negative 1, go up a little bit, down to the 0, which because it's a multiplicity 2, bounce back up, and then eventually head back down towards the 1. So you should have a graph that is symmetrical over the y-axis, which means equal size humps. And again, you know that because these are equidistant from 0, 0. This is, of course, also known as an even function because it has y-axis symmetry. And you know that looking at the fact that all of the exponents are even powered. That's how you know that it is an even function. Not an even degree, but an even function, which again means y-axis symmetry. So a couple more. 2x to the 4th minus 2x squared minus 40. Again, things you might want to answer right from the start. So that is even positive, which means this is an up-up situation. Y-intercept, 0, negative 40. Factor out the 2. That's going to give me x to the 4th minus x squared minus 20. X to the 4th, you're going to factor that as quadratic form. As long as you have an even degree, half that power, and then nothing, you can factor it the same way you would a regular quadratic, but instead of x and x, you're going to factor it as x squared and x squared. Factors of negative 20 that add up to be negative 1, that's going to be minus 5 and positive 4. If you now set this equal to 0 to find the x-intercepts, be careful. If you set 2 equal to 0, that doesn't give you any answers. You can't have any answers if there are no x's. If you set x squared minus 5 equal to 0, you're going to get x squared equals 5, which take the square root, don't forget the plus or minus, you're going to get positive 5 and negative 5, both as an answer once. So they each have a multiplicity of 1, which again, I would be careful, cautious of writing plus or minus, because I do think some people get confused. What happens if you set x squared plus 4 equal to 0? Well, that means you're going to get x squared equals negative 4. And of course, if you were to take the square root, you're going to get plus or minus. The square root of negative 4 is 2i. That's imaginary. How do you graph imaginary things? Well, you don't. So no worries if that happens. You can still graph. You just have to think about what the implications are. So again, 0, negative 40 is some point way down here. Please don't count 40 tick marks. An estimation is just fine. The square root of 5 has a decimal approximation of 2.23. So 2.23 and negative 2.23. This has end behavior up, up. Radical 5 and negative radical 5, those are multiplicity 1s, which means you're going to cross, go down to the y-axis. come back up, and then cross. Again, yours should be a bit smoother than mine, but this is what the graph looks like. Couple things to notice here. So even though this is a quartic, there's only one turn, and remember, that's fine. You can have fewer turns. You just can't ever have more than one less than the degree. Secondly, because all of the exponents are even powered, this is again an even function, meaning it has y-axis symmetry, which again, you know, because of the fact that the x-intercepts are equidistant on both sides. One last graph here, and notice that this is in factored form. So when you're in factored form compared to standard form, there are some things that are easier, and then there are some things that are slightly harder. So just make sure you know how to do it in all cases. If you add up all the x's, you get a total of 4, which is even. Look out front, and of course, that's positive. And again, look to see if there were any negatives hiding throughout the way in terms of the x's. But even positive means we're looking at an up-up situation. Very easy from factored form to get the x-intercepts. It would be -2 with a multiplicity of 2 and +3 with a multiplicity of 2. To find the y-intercept, you would have to put a 0 in for all the x's, which would give you 2 squared times -3 squared. That would be 4 times 9, which gives you a y-intercept of +36. So again, just make sure you're able to do it whether it is factored or standard form. So 0.36 is again somewhere up here, -2 compared to 3. That's how we know this is not going to be an even function because they are not equidistant. And behavior is still up, up. And because these are multiplicity 2s, you're going to be bouncing at both. So coming from the positive, bounce at the -2, up to the y-intercept, down back to the 3, and then ending facing up. And again, exactly how high do you go? We're going to find that shortly, but for now, just a sketch is more than sufficient. Finally, the last couple problems, make sure that you could work in reverse. So let's say that I ask you to find me a polynomial that has the zeros of -5 and 5. You have to call this something. Y equals f of x equals g of x equals, doesn't matter. If you have an x-intercept of -4, that of course means that you have a factor of x plus 4, and +5 would equate to -5, so x minus 5. So that is one potential answer. There's infinitely many answers depending on what I put out front. 5, 6, 20, -300. A lot of times to indicate the fact that there are infinitely many answers, we put an A out front. And again, that's an A, not a 9. That A means that it can be anything. And so sometimes you actually have to solve for it. Sometimes you can just leave it as an A. And if it doesn't specify, you could literally make it whatever you want. One last example, same idea here. So you have to have the given zeros, 0 and 5, but then it says that you have to have a degree of 3. So let's call this one f of x. In order for you to have a 0, you would have to have an x. In order for there to be a 5, you'd have to have an x minus 5. If you leave this equation as is, you're only going to get a degree of 2. So how do you increase the degree but don't change the roots? You have to add multiplicity. So I could add a 2 here. Instead, I could have added a 2 on the x minus 5. Doesn't matter where you put it as long as the total degree winds up being 3. Again, there's infinitely many answers depending on what you put out front. This would be fine. You could put a 6, a -20, or you could just put an A out front to indicate that it could be anything. And again, sooner rather than later, we will actually solve for that A. You'd have to have more information, but for now, just make sure you know that it's a thing. So here's homework number 13, and I separated it into groups instead of just going in order. So the first 7 problems, I want you to graph those. So ignore whatever the directions in the book say, and you're just going to go ahead and graph them like we did in class. So try not to use the graphing calculator unless you want to check it, but I would like you to find the x-intercepts, the y-intercepts, and the end behavior. Then the last set of questions, these are the ones that are asking you to work in reverse or to do some other stuff. Okay, so thanks very much for tuning in, guys, and we will catch you next time.